Good morning, everyone. I'm happy to be here, and it's a pleasure to give you an introduction about the recent advancements in reactive transport modeling within GeoDict 2025, and also to give you a preview of what we are working on in the future releases. My talk is about reactive transport in porous media, and I would first like to focus on transport and come later to the reaction. And to do that, I would like to briefly recall the basic transport mechanisms that we have. So we start on the particle scale, and we assume that we have a fluid, a so-called solvent, and in the solvent we have particles, like, for example, here a cloud of particles at time t0. And if the fluid has a body movement, then those particles are transported with the phase, with the fluid, to some other place, and that can be illustrated like this, like here, and at some point T1, the particles end up somewhere else. This transport mechanism is called advection. The second main transport mechanism is diffusion. Diffusion means that you have on a particle scale Brownian motion, you have random molecular motion. So every particle goes into a random direction, described by a coefficient d, by the diffusivity. And this diffusion smears out particle clouds, I would say. And this is already well established in GeoDict within the module addict. So addict is actually for the prediction of advection and diffusion. And there's a command track particles, and track particles does exactly that. Now in GeoDict 2025, we're following instead a continuum mechanics approach, which means we don't consider particles, we instead consider concentrations given, for instance, in moles per cubic meters. And instead of tracking particles, we solve partial differential equations. For example, for advection, we have here the advection equation, also including the flow field as a coefficient. And as an academic example, imagine you have the concentration plotted against the spatial domain, and you start with a block of concentration at time t0. And you have a constant flow velocity in one direction, and this concentration block would end up somewhere here on the right. The amount of advection that you have in a simulation is quantified with a dimensionless number, the so-called Courant number. So the global Courant number of, for example, 0.5 tells you that this block is transported in half of the domain length. The second transport mechanism would be diffusion. Here you see the diffusion equation. This coefficient d shows up again here in this position. And what it does, it smears out concentration profiles in time. Of course, if you drive the time to infinity, you would end up with a constant concentration everywhere. And you can also, of course, combine these two mechanisms. Then you have the advection-diffusion equation. So for the diffusion equation, you also have a dimensionless number, which is the Fourier number. So we have the Courant number, the Fourier number, and then if you divide the Courant number by the Fourier number, you get the so-called Peclet number, and the Peclet number gives you a ratio of advection and diffusion. So if you have pure advection, you have Peclet number of infinity. If you have only diffusion, you have a Peclet number of 0. And GeoDict 2025 is able to cover all this range of Peclet numbers. So which means you can also compute pure advection or pure diffusion, or anything in between. So as a first benchmark to exemplify advection, we have to solve the Stokes equation. The Stokes equation produces a stationary flow field. As you see here, there's no time derivative in this equation. So you receive the velocity, the fluid velocity, and the pressure. The fluid velocity ends up then as a coefficient in the advection equation. Here on the lower left, actually you don't see my mouse pointer, but on the lower left you have the velocity magnitude, and on the right you see the concentration that flows into the domain from top to bottom. So you can specify, you can quantify the inflow concentration at the top boundary. You could also define an initial concentration profile, which is here 0 in this case, but this is all possible, and this is like the standard default setting in GeoDict 2025. What you see is actually a pore space, a slice of a Berea sandstone. We compared these results with the track particles command. So the new command is called transport concentration. The old command with particles is called track particles. Two completely different approaches. They use the same flow field here, and we compared the particles with the concentration profile, and qualitatively they are comparable, which is a good thing. So now the philosophical question is, why do we actually implement a new solver in a continuum mechanics framework? And the answer is there are many physical or chemical processes that can be modeled easier with one methodology, and others are easier to model with the other methodology. So, for example, adsorption processes are easier to model with particles, while reactions, I would say, are easier to model with a continuum mechanics framework on bottom. Now, this is another example of the default setting in GeoDict 2025. You have a non-woven structure, for instance, and what the solver does, it introduces an inflow concentration and top boundary and transports it through this structure here. The concentration at some point reaches the outflow boundary, and in your report you will get a breakthrough curve that gives you the average outflow concentration at the bottom boundary in this case. But there are also many other data in the report. Okay, so to summarize this transport solver of GeoDict 2025, so it is able to handle the whole range of Peclet numbers from 0 to infinity in a stable fashion, so you will not receive any artifacts or oscillations. As a user, you don't have to take care of any time stepping sizes, for instance. This is all what the solver does for you. You just give the solver an error bound, and the solver takes care of the time stepping. And the solver, the discretization is designed in a way that it's locally mass conservative, which means that all mass that flows from one cell to the other cell is not lost, or there's also no gain of artificial mass. And this also implies global mass conservation, by the way. Then we have a nice property, bound preservation. This implies, for instance, non-negativity of concentrations. So you will never receive negative concentrations. If you do, tell us, then it's a bug, obviously. We also verify our solvers, both for diffusion and for advection and for mixtures, by comparing our numerical solution against analytical solutions. So we run so-called grid convergence tests, and we then observe that the discretization order is decreased in a certain order, thus verifying the numerical scheme. And the transport solver supports irregular grids. What I mean with the irregular grid is if you have a flow field and you have the grid refinement activated in the Lear solver, then the Lear solver coarsens the grid, and then you end up with an irregular grid, and the transport solver can work on this irregular grid. What it cannot do yet is refinement in a dynamic way at the concentration front. Like, for example, say you have a very sharp concentration front and you transport it through a fluid phase, then maybe you want to refine right at the front because the numerical error is the biggest there. This is a feature that will be introduced in GeoDict 2026. So we are already working on it. Okay, let's speak now a little bit about modeling of reactions. To give you a big overview, I tried to classify reactions out of the view of a mathematical modeling person. So you can categorize reactions in many different ways, and I picked out some of them. First, scale consideration. If you look at the upper left, you see a domain that consists of a phase A in blue and a phase B in red. And phase A could be, for example, a fluid phase. Phase B could be a fluid phase or a solid phase or even a gaseous phase. It's also fluid. I mean, phase A could be liquid and phase B a gas, for example. And then there is a transition area, the interface area here in green, that is in between those phases. This is what I call pore scale, or there are also other names, but I label it now pore scale. So you have explicitly resolved phases. You also see the structure of the phases, and as opposite to that, there's the Darcy scale, where you treat the medium as an average medium, and you have effective quantities such as the permeability or the porosity or the reactive surface area that represent the microstructure that is no longer resolved. So you have to be aware of what you actually want to do first, if you are on the pore scale side or on the Darcy scale side. And of course, in GeoDict, the Darcy scale that I illustrated here does not have to cover the whole domain. It can also happen that you have only certain voxels that represent Darcy scales, like with a subvoxel structure, as we call it. Then second, phase involvement. Might happen, you have to see where your reaction actually occurs that you're interested in. Does it occur in a pure phase? Then, like for example, here in phase A, then we call this a homogeneous reaction, or does it occur in between two different phases, like here at the interface illustrated in green, then we would label that heterogeneous reaction. So phase involvement is the second class. The third classes are, I actually didn't talk about what actually reacts. So usually you have chemical species, solutes that are represented by concentration inside a solvent fluid, here illustrated as discs and triangles. They can react in a pure phase, or sometimes it also happens that the whole phase reacts. Like if you think of mineral dissolution and precipitation processes, that is something that where the whole phase, or where the species actually represents the phase. So the modeling challenge here is that a species in concentration does not have a volume, by the way, just as a remark. But a phase obviously has a volume. And for the reaction speed, if the reaction happens on the same time scale as the transport, then we label these reactions kinetic reactions, and those kinetic reactions can be either irreversible, which means they only go in one direction, or they are reversible, then they have a forward and a backward reaction, or the reactions they are so fast that we assume chemical equilibrium. In this case, they're always reversible. And mathematically, the kinetic reactions are represented by an ODE, by an ordinary differential equation, which then has to be merged into the partial differential equation for transport, while the equilibrium reactions are represented by linear algebra relationships. So basically, for every equilibrium reaction, you can kick out one species out of your problem. So it's easier to deal with the equilibrium reactions. So today I would like to show you two very brief benchmarks. The first benchmark deals with a homogeneous reaction inside a fluid phase, and the second benchmark deals with a heterogeneous reaction, however, on the Darcy scale. So the first benchmark for reactive flow looks as follows. We have a flow field. This is the Karman vortex street that I stole from the previous speaker. There's already a flow from top to bottom, and there will be vortices occurring very soon. And what you see actually here is the vorticity. So we have a counterclockwise in blue and clockwise in red. We insert concentration A at the top left boundary and at concentration B at the top right boundary. And those species A and B, they react here. They react to C. So 1 mole of A and 1 mole of B gives 1 mole of C. Why I do that? The reaction can only occur when both concentrations for A and B are non-trivial, which means that they're non-zero. And this is something that you see very well in the mathematical equation. So you have here the Navier-Stokes equation for the transient flow field. Transient means that it always changes in time, so it's not stationary. You have here the incompressibility constraint, and here a transport equation for each species concentration. For the concentration of A, B, and C, we have here the advection terms, here the diffusion terms. We could also give them different diffusivities, but it's not interesting here in this case. And here on the right, we have the reaction term, which is in this case also nonlinear. It's a quadratic term. And here you see the concentration of A and the concentration of B have to be both positive in order for the reaction to occur. And then second, you also see mass conservation. So this term here is a negative term for A, a negative term for B, and a positive term for C. This is exactly what represents this very simple benchmark reaction. Okay, now let's look at the simulation. So we have an inflow of concentration A and B. So this is the same domain. It's just for visualization that I have this 3 times. So yeah, so actually this is a very old benchmark that I know from my academia time. But at that time they mixed A and B by diffusion. You know, they had just a regular grid, and the diffusivity was chosen so large that A and B was intersecting, and then you had basically a stream of concentration C somewhere in the domain. Here it's a little bit more interesting because the turbulences are actually causing A and B to mix, and wherever they mix, the concentration can go forward, can consume A and B and produce species C, and that in a mass conservative fashion. So both the transport and the concentration are all mass conservative. Okay, so the next benchmark I would like to show you is a benchmark of a fuel cell, of a PEM fuel cell. It's a proof of concept, so we don't use it for prediction. We're far away from that, I think, or not so far away from that, but it's a first step towards prediction. But what's special here is that I use realistic data in order to demonstrate that the solvers are actually stable. In this benchmark, we are simulating the oxygen and the water vapor transport through the cathode side of a fuel cell. The oxygen is reduced with this oxygen reduction reaction to produce water vapor. We make some modeling assumptions that I will show in a second. And the oxygen travels through a channel through the gas diffusion layer, which is a coarse non-woven structure, into the microporous layer, where you mainly have diffusion as transport mechanism, and into the catalyst layer. And in the catalyst layer, you actually have the reaction. Now let's have a closer look at the structure. So here you have a section of the fuel cell, and on the left you have a zoom in here of this part of the fuel cell. What's special here is that we actually geometrically resolve the gas diffusion layer, which consists of these red fibers and the green binder. The microporous layer and the catalyst layer are also porous media, but those we model in a average fashion. So this would correspond to the Darcy scale that I was mentioning. And it has a big advantage for modeling because the reactions actually, they occur on the surface of the catalyst, next to platinum particles. However, if I model it that way, then first of all, I don't have to struggle to resolve the geometry. And second, the reactions are suddenly volumetric reactions and no longer surface reactions, while the surface is represented with a effective parameter, the reactive surface area, which can be, for example, expressed as a function of porosity, depending on the material. All right, so, and I was told that fuel cells work actually in a compressed state. Sebastian Rief helped me to compress this fuel cell, and we're actually doing the simulation on the compressed fuel cell. This is done with GeoDict. And just for the modeling assumptions, to repeat it, so we have a constant airflow from the left side to the right side. The solvent fluid is air. The air has a certain oxygen concentration. So the solutes are oxygen and water vapor. We assume that there is no water in liquid form, so we assume that there's no condensation processes happening. We further assume that there's always enough supply of protons and electrons in the catalyst layer. This is, by the way, something that can be relaxed in the future, and we actually can simulate the transport through isomers and so on. We assume that there is a constant temperature. Constant pressure is not true. This is an error on a slide. Yeah, and we assume the microporous layer and the catalyst layer unresolved. So then we end up with two transport equations, and each of those transport equations is solved with the transport solver of GeoDict 2025, while the reaction is actually, I would say, like tinkered with a Python script, tinkered in quotes. I will come to that. It's an advantage and a disadvantage. Reactions will be included in a Lear solver in 2026, but this is just a proof of concept to demonstrate that it actually would work if we do that. So what you see here is I removed the channel geometry. This is basically the solid, and this is the H2O gas concentration as an ISO value that is generated when oxygen flows through the fuel cell. So this is a dynamic simulation. So the water vapor is constantly transported out of the domain. And since we're having stationary boundary conditions in this scenario and stationary data, the solution will approach a stationary state. And this, what you just see here, is the stationary state, the stationary water vapor profile that would occur in this case. Yeah, I mean, you see here, for example, that you have some higher vapor concentration on the right of the domain and some lower on the left of the domain. This is just because of the fact that there is an inflow from the left to the right. So I think as a proof of concept, this is acceptable. As I said, so reactions are not included in 2025. However, GeoDict is designed in a modular way. And we actually use the Python scripting, and we're calling different GeoDict commands within the Python script. So first we computed the deformation with ElastoDict. Then second, we computed the stationary flow field with FlowDict. And then we loop over so-called time batches. So we decompose the physical time into time batches. And in each time batch, we call the transport solver for the oxygen and for the water vapor concentration. And then inside the Python script, we coded the reaction, and we call visualization routines in GeoDict and write images. And then at the end, we combine those images to a video. So as a summary and an outlook, the solute transport command in addict is available in GeoDict 2025. It basically has a very similar dialogue as the track particles command. It can simulate the transport of one solute species, and Peclet number between 0 and infinity are applicable. Yeah, and if you would like to add reactions, then you have to do it yourself with Python scripting. While in 2026 we are planning to support multiple solute species. Of course, then those inherit all the features from the single species transport solver. We will add some kinetic reactions, solute-solute reactions, so to say, aqueous reactions. They can be, out of this perspective of a developer, they can be arbitrarily complex, those reactions. But it would help us, of course, if you would tell us which kind of reactions you're interested in, such that we can include them into the Lear solver. And then last but not least, we also have in mind that we allow for heterogeneous reactions where the solid phase actually might change during the reaction process. Okay, thank you very much for your attention. I'm open for questions.